So in Chem 102, there are many concepts that you need to know, such as entropy, equilibrium constants, Gibbs free energy at a standard, as well as Boltzmann's constant. Now, where you want to start is by looking at phase space. Now, phase space is looking into, I can't point, but a system and how the system releases energy, or at least releases its particles into the surroundings, and eventually these surroundings will lead into the universe. Now, the way that the system releases itself into the surroundings and the universe is through equilibrium, and this is explained through entropy. Now, entropy is equal to Boltzmann's constant times the log of ignorance, multiplicity, or work, however you want to state it. Now, the Boltzmann constant is R over NA, and R is the ideal gas constant over Avogadro's number, and then if you wanted a specific number, that would come out to 1.3 times 10 to the negative 23rd power joules over kelvins. And so that's Boltzmann's constant. And coming back to entropy, entropy is the movement of energy from a system dispersing into the surroundings. Now, the way that energy is released into the surroundings is through equilibrium. And equilibrium can be understood through its constants. Now, K would be the equilibrium constant, and there's two ways that you can identify it. It's through concentration and through pressure. Kc, which is the concentration, determines for solutions, as for Kp, which is pressure, has to deal with gases. Now, looking at a regular chemical equation at equilibrium, you have the reactants A plus B going forward into the products, which are C and D. Sometimes you may go back, or not sometimes, but all times, the reaction will also be going backwards or in reverse, which is Kr, into the A and B. So A and B would then turn into the products, and C and D would be the reactants. Now, to put that into Kc for concentrations or for solutions, you would have the molarity of C and D, which are the products, over the molarity of A and B, which are the reactants. So it's also known as Kf over Kr, which is then equal to Kc. Now, sometimes you'll still have gases, and so you have to change molarity into pressure. And so you use the ideal gas law, which is PV equals to nRT, and if you change it, you would have now P over RT is equal to N over V, and N over V is molarity. Now, if you want to change this P over RT into the molarity of the Kc, you would then have Pc times Pd over Pa and Pb. The exponents Cd and Ab would be the coefficients for the reactants and the products. Coming back to this, you would still have to times it by the RT, which would be from the P over RT, and you can then change the equation into Pc times Pd over Pa over Pa times Pb, and this is times by 1 over RT to the power of Cd, which is the top, which are the products, minus Ab, which are the reactants. Now, you can change the P's back into the constant, which is K over P, or Kp, I mean. Kp is over RT is to the coefficients as the exponents. And then you can change the difference in the coefficients into the delta n. Now, bringing back Kc, since this is where we're deriving it from, Kc is equal to Kp over RT of delta N, and you want Kp by itself, so you have Kp is equal to Kc times RT to the delta N. And this is all to show the connection between Kc and Kp, which are still the equilibrium constants. Now at times for phase space, that you're not moving energy from the system into the surroundings, but now it's moving from the surroundings into the system. And mostly you can say it's the universe into the system. And this can be understood through Gibbs free energy. Now Gibbs free energy can be considered internal energy or chemical potential. And thinking of potential, it's the potential to do work, or the potential to do, or the potential energy that can be used. So, looking into this, the delta G, which is Gibbs free energy, is if the energy is negative, which means that energy is not going into the system, is that it's being dispersed, that means that the universe will be gaining energy. Or if it's the opposite, if the universe is losing energy, that means that the Gibbs free energy, or the internal energy, is being gained in the system. A way to specifically to look into Gibbs free energy is that Gibbs free energy is equal to enthalpy minus work. Now starting off with work is an extension of entropy, and that's the way that energy is dispersed into the system. So of course, if energy is being dispersed into the system, that means that Gibbs free energy is decreasing. Now for enthalpy, enthalpy works with heat, and heat has to do with pressure and temperature. Now, temperature and pressure, because the amount of energy released is going to be the temperature, and then that temperature is, or that heat is going to affect the molecules in the air, which then affects the pressure. Now, Gibbs free energy, again, just relating it, is that Gibbs free energy is equal to enthalpy, which has to do with the heat, right? So backtrack. Enthalpy, since it has to do with heat, the amount of heat released would be the amount of energy that's being released. And if the heat was minimal, or at least there's like it's becoming a cold reaction or an endothermic action, that means that energy is being gained, or the system is gaining energy. So endothermic is when Gibbs free energy is increasing, when the system is gaining energy. As for an exothermic reaction, which is releasing energy into the system. Okay, and so delta G, now relating to delta G standard, is for people to be able to determine the amount of energy that a system either gains or releases at a set pressure and a set time. And so this will help people determine those specifics. So those are the concepts of delta G standard, entropy, and the equilibrium constants, and also Boltzmann's constant.